This is the Pre-AP Chemistry Spring 2014 review for the subjective final. With your hostess, Mrs. Irons. The first thing that we're going to look at is the list of polyatomic ions. We're going to review the cations first. Cations are positive ions. The trick to remember that is there is a T in the middle of the word, and the T makes a plus sign. There are only two. Ammonium is the first one. And the chemical formula for that is NH4 plus. And hydronium is the second one. The formula for that is H3O plus. Next, we'll move to the anions. Anions are negative ions. The first list has a -1 charge. The first one is bicarbonate or hydrogen carbonate, and the chemical formula is HCO3 minus. Then cyanide, which is Cn minus. Hydroxide, OH minus. Nitrate is NO3 minus. Nitrite is NO2 minus. Perchlorate is ClO4 minus. And permanganate is MnO4 minus. The anions with a -2 charge are carbonate, which is CO3 2 minus. Chromate, CrO4 2 minus. Dichromate, Cr2O7 2 minus. Sulfate, which is SO4 2 minus. Sulfite, which is SO3 2 minus. And thiosulfate, which is S2O3 2 minus. And the only anion with a -3 charge is phosphate, which is PO4 3 minus. We're going to determine the molar mass of a product next. You need to use your periodic table to determine the molar mass. The example we're going to look at is ammonium, which is NH3 plus. We're going to use the periodic table to see what the mass of nitrogen is and the mass of hydrogen. And we're also going to multiply hydrogen times 3 because right here in the chemical formula it tells us that we have 3 hydrogens. Now 1.01 times 3 is 3.03. Now I'm going to add these numbers together, and I get 17.04 for the molar mass of ammonium. Looking at the periodic table, element number 7 right here is nitrogen, and it has 14.01 for its mass, and hydrogen has 1.01 for its mass. Next, you need to determine the number of shared electrons between atoms in a molecule by looking at a diagram. There's 2 diagrams here. The first one, the one on the left, is water, and you'll notice that there's 2 lines, one between each hydrogen and the oxygen. This single bond is represented by this line here and this line here. There are 2 electrons shared in each line, so that means that there are a total of 4 shared electrons. The one on the right is the benzene ring. The double bond is represented by 2 lines, and there's 4 electrons shared in every set of double bonds. Next, you need to explain why a catalyzed reaction occurs at a faster rate in terms of activation energy. Now, I wasn't exactly sure how to answer this, so I did what any good pre-AP chemistry student would do, and I Googled it. I got to about.com's chemistry section, and the catalyst definition, a catalyst is a substance that increases the rate of a chemical reaction by reducing the activation energy, but which is left unchanged by the reaction. Notice there's a little diagram on the bottom right-hand corner. This diagram says a catalyst permits a different energy pathway for a chemical reaction which has a lower activation energy. The catalyst is not consumed in the chemical reaction. If you look at the original reaction, look at the black line, it follows this path. If we add a catalyst to the reaction, it follows this red path, but you see it takes quite a bit less energy to do that, so it's beneficial to use a catalyst. Next, explain how these types of reactions occur. The first one is an addition or a combination reaction. In this, you can see we have A plus B yields AB. You have two reactants and one product. The two are combined, thus the name combination reaction, or they're added together, thus the name addition reaction. Next is a decomposition reaction. In a decomposition reaction, you have one reactant and two or more products. Usually the products are water, carbon dioxide as a gas, or oxygen as a gas. In this example, you see you have carbonic acid yields water and carbon dioxide. Next is a single replacement. Looking at the figure, we can see that AB plus C yields A plus BC. The single compound that moved was B. It went with its bonding to the chemical AB over to C, so it's a single replacement because only one compound moves. In a double replacement, there's also two reactants and two products, and it plays a switcheroo, as you can see with the yellow and the red arrows. The silver and the sodium switch places. So the silver nitrate and the sodium chloride yield silver chloride and sodium nitrate. Determine the molarity in an acid-base titration. The example problem says a 10.0 milliliter sample of hydrochloric acid requires 16.5 milliliters of 0.500 molar sodium hydroxide to reach the endpoint of the titration. What is the molarity of the acid solution? The formula for this is fairly simple. If you take the molarity of the acid times the volume of the acid, it gives you the molarity of the base times the volume of the base. If we look in the problem, this is our acid, hydrochloric acid, and we have 10 milliliters of that. So I can plug that in for my volume of acid. And then here, sodium hydroxide is our base. We have 16.5 milliliters, and it's 0.5 molar. Now, I'm not using significant figures in the calculations. So 0.5 times 16.5, to get the n by itself, I need to divide both sides by 10. So the molarity of my acid is 0.825 molar. Next, write a formula for an acid-base neutralization. We're going to combine sulfuric acid and sodium hydroxide. The chemical formula for sulfuric acid is H2SO4, and the chemical formula for sodium hydroxide is NaOH. Okay, first I'm going to write a skeleton equation. So I have H2SO4 plus NaOH yields, and I know that the two things that it comes up with is a water and a salt. So I'm going to go ahead and write down water, H2O, and I'm going to break the sulfuric acid into ions and the sodium hydroxide into ions. The two ions for sulfuric acid are hydrogen and sulfate. I know sulfate has a 2- charge because right here the hydrogen has a 2 subscript, and you switch places the ionic charges for the subscripts. Sodium hydroxide breaks into Na plus and OH minus. Now in order to get water, I've used the hydrogen and the OH minus. So that leaves sulfate and sodium. So I'm going to write those. Sodium's listed first because it's the cation. I know it has a 2 subscript and then followed by SO4. Now I need to balance my equation. First, I'm going to look at how many hydrogens I have on the left and how many I have on the right. I have 3 hydrogens on the left and 2 hydrogens on the right. I'm going to save the hydrogens till the end because I always like to use water as the last thing that I balance. Okay, next I'm going to look at the sulfurs. I have 1 on the left and 1 on the right, so far so good. Now I'm going to look at the oxygens. I have 5 oxygens on the left and 5 on the right. And last, the sodiums. I have 1 sodium on the left, but I have 2 sodiums on the right. So I'm going to put a 2 in front of the sodium hydroxide, and that changes the number of oxygens and hydrogens I have. I have 6 oxygens now, and 1, 2, 3, 4 hydrogens. Now in order for my hydrogens and oxygens to balance on the right, I'm going to change this to a 2. So that changes my hydrogens to 4 and my oxygens to 6. If you check, all the numbers are now balanced. Except I forgot to put that right there. Next, write chemical names for common household chemicals. The first example is salt, which is sodium chloride. And the chemical formula is NaCl. Next is baking soda, which is sodium bicarbonate. And the chemical formula for this is NaHCO3. The next example is vinegar, which is acetic acid. And the chemical formula for this is HC2H3O2. And last is Epsom salt, which is magnesium chloride. And the chemical formula for this is MgCl2. Now we're going to determine percent composition. Again, you're going to have to use the periodic table to determine mass. We're going to look at baking soda for our example. Okay, remember baking soda is NaHCO3. So I need to find the total mass of NaHC and then 3 times oxygens because we have this 3